Yes, thank you very much. So today I want to talk to you about smooth analysis and congestion games. And my plan is to very quickly at a high level introduce you to both of these topics and then mention our main result and have a very short discussion about this. Okay, so congestion games, before giving you the formal definition, let me start with a simple example just to get you familiar with the model. The intuition here is that congestion games are used to model situations where a set of agents is competing over a common set of resources. That's the idea here. So here, for example, think about that we have these four resources represented by these squares. And we have two players, player one, player two. And player one has two possible strategies. They can either play the two top resources or the two bottom ones. And then player two can either play the two left ones or the two right ones. I know this looks like a biomatrix games with rows and columns. It has absolutely no relation, right? This is just of the graphical representation. So if your mind goes there, just and also associated with each resource, we have a cost. We have a cost function. And again, here these are not fractions. This is a standard notation. These are just two numbers for each resource that tells you what is the delay, the latency in this resource if one or two players play that resource. Okay. So, for example, let's see what is a meaningful outcome of such a situation. Let's say player one, the blue player, plays top, the top strategy, and player two, the yellow, plays the left. Then you see that we have a congestion of 2 at the top left resource. So both players are going to suffer 10. Player 2 is going to only suffer 2 because there's only one load in this resource. The blue player, player 1, is going to suffer 2 from the top right, and no one is playing the bottom right, so there's no delay there. And what is the cost that the players are experiencing? Just the sum over the cost they're experiencing through the resources they're playing. So both players here play 12, okay? And we're wondering, is this a stable state? What's going to happen? And you can see that, for example, player 1 has an incentive to deviate and go right, because then from 12, they can go to 11, because it's not going to be 7 and 4, okay? And similarly now, notice that also the cost of the first player improved, okay? But we don't care for that, just player 2 unilaterally deviated. And now we can see that player 1 wants to deviate now and go from 8 to 7. Okay, and now we're at the situation where this kind of unilateral deviations, they have no improvement for the players. So this is what we call an equilibrium, and this is a stable state here. Okay? So these are the kind of situations that we want to model. These are the kind of stable states we want to find. And here is the more formal definition of a congestion game. We have a set of players, m resources. Each resource has a cost function that takes as argument an integer from 1 to n, representing how many players are playing this resource. And we get a non-negative cost. Strategy sets, okay? This player has a strategy set, which is collection of resources, then the power set of the resources. And what's an outcome of the game? A strategy profile. It's just a collection of strategies, one strategy for each player. This is an outcome, a state of the game. And given such an outcome, what is the cost that each player is experiencing? As I said, the cost of player I, we just sum over all the resources that the player is playing are in SI. And then you evaluate the cost function on the load on this resource, which is how many players are playing this resource. Okay, and what is an equilibrium? As I said, standard definition. And here I'm only going to talk in this talk only about pure equilibria. So it's an outcome where no player I would like to deviate to an alternative strategy SI prime, because then they will experience more cost. Now, good news from a similar result from Rosenthal, pure equilibria always exist in these games. Okay, again, I emphasize this is pure, not mixed equilibria. So they also exist from Rosenthal. Bad news from complexity, this is a PLS hard problem to find an exact pure equilibrium. I don't know how many of you are familiar with PLS, so this talk is enough, it's a good enough approximation. This is not very accurate, but think about the class that lies between P and NP. So similar to PPAD that Harambos talked today and Themis talked yesterday, it's a total search class, right? Think about it, this PLS, The acronym is polynomial local search. It was introduced by Johnson and Giannakopoulos. It tells us that it is as hard as any local optimization problem. Okay, think it like this. And I'm definitely not a complexity theorist, but people who know these things better than I do, they think, you know, this is a sign of hardness. Okay, we believe this is not this. So there's a separation from the class P. Okay, so this is bad news. Okay, what we do when we have this kind of things in computer science, let's go for approximation. Okay, let's relax our notion of equilibrium. Let's try to find epsilon approximate equilibria, epsilon PNAs, I'm going to call them. Okay, we just multiply with 1 plus epsilon, the inequality of the equilibrium. Good news, of course, they still exist, right? Because every exact equilibrium is also an approximate. But bad news, the problem remains hard. And actually, it's a very strong hardness. It's for any constant epsilon. Okay, so this is very bad news. Okay, so this is the topic of our paper. Let's try to find this approximate equilibria. So we're going to use a particular dynamic, okay, which is going to better response dynamics. So think about what we did at the example that each player was playing best responses. Okay, that's the idea here. Let's go a little bit deeper on the existence result by Rosenthal. Okay, how Rosenthal saw the existence result. How do we get it? By using this potential function. So Rosenthal defined this potential. In each outcome, you just you sum over all resources, and you sum the cost from 1 up to the actual load of the resource. Okay, it sounds a little bit weird if you've never seen that before. Okay, but it really works, and it does. It does the trick, so it has this beautiful property. So if you take any player I and you deviate to any strategy, the amount that you improve or the change, it can be captured by this function. Okay, so what this means, keep improving this function, okay, minimizing it. If you cannot minimize it further, this is exactly a pure mass equilibrium. And this is exactly how Rosenthal proves existence. And actually, this is why we can put the problem in the PLS class, and it's a local optimization problem. Okay? So, but this also gives us a very natural algorithm, because improving the potential means better response. And we need to be careful that each pivoting step, it's not only how many steps, that you can do this best response in polynomial time, and we can look for all the representations that we use. And this is why actually you are in PLS. Okay, you are essentially a local optimization problem. Now, all of these dynamics, you can do them also for epsilon, okay? So you can do epsilon based response dynamics. You just check if you are in epsilon equilibrium. If you are not, it means you can improve more than epsilon. Good. Now, the other component of the title, smooth analysis. Again, I don't know if you are familiar, but there's a very interesting, this is a big deal. There's a very well-known success story here. This was introduced in the seminal work by Spielman and Teng. The latter won the Gödel Prize for the contribution, I think, in 2008. The story here is for the simplex algorithm for solving linear problems. Okay, this is the de facto algorithm for solving linear programs. A lot of people use it in practice. We know it performs well in practice, but in theory, we have a counterexample. The Clemente cube that it tells us that in theory, simplex it's exponentially long. Okay, so how do we compromise these things? How we bring together theory and practice? And actually, the contribution here is the model and the result, of course, right? So what they did is that they said, okay, let's take the traditional worst case input here. You take a linear program, and we're going to introduce some small stochastic noise, right, in the numerical inputs. And we're going to parameterize this by the standard deviation. So think about you add the normal distribution, a Gaussian noise, parameterized by sigma, the standard deviation. And now, in this way, you can very nicely interpolate between various complexity models analysis, right? So, first of all, if you have sigma equals 0, you have no noise, it's the standard worst case analysis. If you have a sigma fixed, it's just a probabilistic analysis model, right? You have an expectation analysis. And what we like here, smoothness, it is not exactly in between, it's actually in between, and I would say towards worst case. So, we want to take sigma going to 0. But we care about the behavior, okay? So you are almost worst case, but you want to see how your running time is in this region, okay? So in another word, how powerful your adversary should be, what's the accuracy of your adversary in order to kill you, and it gives you exponentially bad inputs, okay? That's the idea. And it turns out that simplex is now polynomial smooth running time. But what is smooth now means? Polynomial on the input side, so the traditional worst case analysis, and 1 over sigma, okay? So like the accuracy of this noise. And now we do expectation, okay? It's the expected running time with respect to this randomness. Now, how we translate this to congestion games? We're going to use slightly different, it's essentially the same motivation model, which is inspired by how we do this in many discrete optimization, smooth analysis. So for example, if you're familiar with the local max-cut literature that recently has some impressive results. So we borrow from there the model, and actually congestion game smooth analysis has been done in another recent paper of ours, which was just presented in ICALP, I think maybe yesterday. Yeah. And one of the co-authors is Themis, who is here now. Okay, so what we do there, so think about the representation model that we have these resource costs, right? C evaluated on the load. You're just going to go there and think that these are not given fixed in the worst case, but they are random variables. Okay, and what we do, they are independent random variables, and we assume that their densities, the density function, so these are continuous random variables. They are defined in 0, 1. This is just a normalization, the one here. But you assume that the density is upper bounded by a parameter phi. Okay, so phi is essentially 1 over sigma here. This is the standard way that we do smooth analysis in discrete optimization. Okay, and notice that this is at least 1. Okay, if it is 1, it's essentially a uniform distribution. You can think about it. Right? And what we want to do here, we do running time analysis in expectation with all this randomness, and good results. Polynomial means that you are polynomial on the input size and phi now. Okay, it's not 1 over sigma. Phi is actually a parameter that goes to infinity. Okay, as phi goes to infinity, you actually allow a lot of concentration, so the density can go very up, so you can concentrate your mass around the worst case. Good. Okay, so what is our main result? So our main result is an FPTAS essentially for the problem, but let me tell you exactly what we mean by an FPTAS here. It means that give me the accuracy that you want. You want an epsilon approximate equilibrium, okay? If you run epsilon better response dynamics, and this is any, so start everywhere you want, and if you have multiple improvements, epsilon, take any you want. It's going to converge at an epsilon approximate pure mass equilibrium at most that many number of states, which is polynomial in the number of players n, the number of resources m, phi, which is the smoothness, and 1 over epsilon. Okay, the accuracy. Again, it's just a reminder of what I said, what are all these numbers, and just to make sure that I'm not hiding any creepy, constants here and exponents, the actual result is like this, for example, for general congestion games, okay? N squared, n cubed, and just linearly the phi. Now, there are different models that you can represent congestion games, okay? This is for general congestion games. But because the result is kind of, simple in a way, clean and transparent, you can actually apply it. For example, notice that the cardinality of the strategy sets, how many strategies you have, does not appear at the result at all. It implicitly appears when you do the pivoting rule. But as long as you can do the pivoting in polynomial time, it's fine. So it applies for network congestion games that are implicitly represented through a graph. So there could be different paths in a graph. So the strategies could be exponentially many. But this result applies for that as long as you can do polynomial time through a shortest path algorithm. And various models that we have in the paper about representation, for example, you can do, and this comes from the literature in congestion games, that you can have different ways to represent this. For example, step functions that you can think about that. I don't give you explicitly the cost functions, but I give you breakpoints and how much you go, right? So it's kind of a non-decreasing. And here the smoothness is with respect to the increase. We don't mess around with the breakpoint, we just mess around with the increase. Polynomial cost function, which is a very popular model in congestion games. I just give you implicitly the cost function with the coefficients of the polynomial, and I just perturb the non-zero coefficients. We don't perturb the zero coefficients. And even cost-sharing games, so decreasing cost functions. Okay, so a over an x, and then we just perturb the cost. Okay, let me give you the high-level idea of the proof, right? I'm going to go into the details, but the idea is that we first give by very standard arguments in congestion games, we bound the length of the sequence linear in 1 over epsilon nm and polynomial in 1 over the minimum cost that you can see. Okay, so technically, because we're normalizing 0, 1, this is like the magnitude of the numbers you can see, kind of a pseudo polynomial result. Okay, actually it's C max over C min, but C max is bounded by 1, so we can get this. Perfect. So if we could notice that it's expected, right? So if we could bound the expectation of 1 over C min, that would be perfect. Okay, and this is what. But if you try to bound this, trivially, it really doesn't work, because someone would think, oh, because it's smooth analysis and C min is just bound, there's some randomness. I cannot give it precisely exponentially small. It would work, but no, actually, it fails miserably if you do the expectation. Even if you take not smooth analysis, a simple uniform distribution in 0, 1, not many, not the mean, just 1, and you take the expectation of the inverse, 1 over x of a uniform variable, it's just the integral of 1 over x, and we know from high school, right? This is infinity. Not only exponentially, it's like, okay? So what we do, there's a very simple trick you can do, again, high school mathematics. Instead of just cap it, like put a threshold of h, minimum of this, and now compute the integral, you are going to see that the integral is 1 plus logarithm of h. So what this tells us, if we can find even an exponential trivial bound on the quantity, you can, because you take the logarithm, you can make it polynomial. And this is how the proof works, okay? And okay, I oversimplified with the example, but this is the technical level that we work, right? If you take many phi smooth random variables, the minimum of the maximum of them, and an exponentially long, large threshold, it becomes polynomial. Okay, and some future directions. Of course, the result is nice in the sense that we had the PLS hardness for epsilon equilibria, and now we have smooth polynomial time. But again, this is for approximate. Okay, what about exact? We don't know. We know it's PLS hard, but we don't have positive results. Could someone prove that exact PNEs have smooth polynomial time? And in doing this, you can consider some more specialized. So the result that I presented is very generic in the sense that you can start from any point, you can do any better response dynamics. But you can think about spatially improving moves. For example, take the best improvement at every step, not better. Start somewhere clever. And another thing, I did local search, but technically you can find an equilibrium through other ways. Okay, you don't have to do local search. You can do some clever centralized, some linear, linear programming, some interior polynomial, anything. Okay, can we even do polytime smooth under this kind of algorithms? Another big deal, but this is challenging because lower bounds. Can you prove that perhaps it cannot be polytime smooth polytime, right? Lower bounds, super polynomial. This is extremely hard, right? So lower bounds in PLS in general, constructed lower bounds in PLS are hard, and even in smooth analysis are very hard. It's very hard to provide negative guarantees in expectation. So yeah, to the best of my knowledge, I just know, I think, one lower bound in smooth analysis, very recent one, and it would not probably apply in this. Another important question, mixed equilibria. Okay, since we find pure equilibria, of course, this is also an approximate mixed equilibria. So this is a positive result also for mixed equilibria. And there's a recent paper by Babichenko and Rubinstein that they prove that, okay, the pure equilibrium, exact pure equilibrium is PLS hard. We know now that the exact mixed equilibrium is CLS hard. So series complete actually. It goes a little bit below the hierarchy, but it's still, we think it might be outside P. But there is hope that since technically this is an easier problem, maybe someone could start by proving smooth polytime for mixed equilibrium. And finally, I think the probabilistic tool that I talked about, although it seems elementary, this idea with just thresholding with some, because it's very abstract, right? So it's not only for this problem. So if you have your favorite problem that you want to do with smooth analysis, and you end up having an expression which is polynomial to the magnitude of the numbers, right? Kind of a pseudo polynomial result. And this, of course, is exponential in the worst case, but maybe in expectation, you can bring it down to polynomial using these techniques. Okay, thank you, and you can find the paper if you want in the website.